Hey everybody. So I guess we get to meet up more than once a week here this week. I'm taking over for doing the video on doing the homework video for the calculator part only this week. Ms. O has posted a video of her doing the ones by hand. We just like to divide labor. No, it's fun. Okay, so anyway, we're gonna start with 38. I will emphasize that you guys had to do 23 and 25. Those were by hand. Again, see my comment before. So going on 38, let's see. On the assignment, it says use a graphing utility. Oops, I haven't cleared that out since I did the video for the lesson. Okay, cool. So we're back at the standard viewing window here. So I am going to graph r equals cosine of 2 theta on my calculator. And again, you guys can do this using Desmos if you like using that on your phone. You literally just type in r equals cos 2, and then you have to spell out theta, or on your phone there might be a theta button, but I know on the computer you actually have to type out theta. So here, looking at that, I see that it is in the format of a rose curve from the lesson that I gave you guys, but since I don't actually have to know that, I just have to type this into my calculator. I can type in cosine of 2 theta, and I can just graph it right there. So I don't like how zoomed out that is. And I don't really like using the zoom in button, so I like to adjust my window just to be able to see it a little bit better. I can see that it looks like the radius of those petals of that rose curve is about 1, so I'm just going to make my x min like -2 to 2, my y min -2, and my y max +2, just so that I can see that rose curve a little bit better. On your homework, you're just going to want to sketch that on your paper. So I mean, whoa. Man, what happened with that pen? This pen is marginally working. Bear with me for 1 second, guys. We're gonna switch over to pink. Alright, cool. So. That works a lot better. Sketching it, I see that at 0, I start at that petal. And I just like matching where the petals go on this. You don't have to, as long as you get what looks like a 4-leaf clover on this. That's all we care about. Alright, good enough graph, right? That's a sketch. It looks essentially like this. And we also wanted to describe it, so we'll just call it a 4-petaled rose curve. And if you wanted to get more in depth on that, you could also identify that the axes split the petals in half instead of going between the petals, just to emphasize that it is a cosine curve. But I don't think the directions ask us to do that. We just have to describe the viewing window and describe the curve. So I guess maybe put a 1, 1, 1, 1. Maybe I can just say my window that I used was from -2 to 2 by -2 to 2. Alright, and that's just x min, x max by y min, y max. Alright, cool. Next I look at here, I've got 6 minus 4 sine theta. My mind immediately goes to one of those Limaçon curves. I know this is going to be a Limaçon. So graphing it, I've got 6 minus 4 sine of theta, and I hit graph, and I don't see anything. Anybody know why I didn't see anything? Well, I'll tell you, it's because my viewing window was way too small. So now I look at this viewing window, I see it goes down to -10 on the y min, so I'm going to make my y min -10, my y max maybe like 3 or something like that. I'm going to have to count over here. 1, 2, 3, 4, 5, 6, 7. I'll make it -8 to 8 for the x's. So -8, 8, -10, like I said, up to 3. And it looks like, ooh, I've got that wonderful Limaçon. If I want to be incredibly picky about it, I could say that it's a dimpled Limaçon, if I want to sound really cool. So again, just graphing it here. I don't care how accurate your graph is. Maybe emphasize that that's up at 2, a max of 3. 1, I'm being a little bit more accurate than I would ever require you guys to be. 6, 7, 8, 9, 10. So I know I go out to, what is that? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So I'm going to go out there. I'm going to go up here. I kind of like bump up a little bit. Those of you who are artists are going to make fun of me for this. 3, 4, 5, 6. And I know I'm going to go over here. Maybe have a little bit of a bump up right here. I just use those points to get my... I'm really picky with myself. Not as picky with you guys. But I just don't like putting out what looks like garbage here. Again, I don't care how accurate your graphs are, and we're not even collecting your homework, so really just looking at it on the graph would be nice. Here, we would say it's just a dimpled lemma. How do we make that little foot on here? I think I got that right. French speakers, you're going to make fun of me for that one. So it's a dimpled limaçon, and my window that I used is, what did we say we used? So x-min -8 up to 8 by y-min, mixing up my words there because I don't talk too good. Alright, there we go. Dimpled limaçon with a window -8 to 8 by -10 to 3. Looking here, I see it's going to be another limaçon. I see that actually my A is bigger than my R, so between 1 and 2, I'm going to say this is going to be another dimpled limaçon, but we don't know for sure. Until, well, actually I do know for sure what it is. 3 minus 2 sine of theta, and we graph, and look, it's a limaçon curve about half as big as the previous limaçon curve. So really, we could zoom in a little bit on that graph if we wanted to, and I'm just directly copying it off of here. I see that dimple is up at 1, the bottom 1, 2, 3, 4, 5. It goes down to 5. 1, 2, 3, 4, 5. But again, I don't give a rat's behind how accurate you are on this. And again, you're not even turning it in, but I am very picky about my own stuff. I like to look smart. It's not enough to be smart. You have to put that out there and just show everybody that you're smarter than they are. Alright, there we go. There's my dimpled limaçon. I'm just going to say it is a dimpled limaçon. And I do not speak French, so again, that foot probably looks horrible. Any French speaker or reader out there. And we can see, I mean, really, I used the same window as before, but just to drill that down a little bit, I could go from -4 to 4 to make this viewing window just a little bit better. And by, what did we say? It went down to -5. -5 up to, I'd say up to 2 to get the tops of those dimples there. And just to show you what I'm talking about here, -4 to 4, whoopsies, 5 to 2. And just see, it just fills it up a little bit more, just to make it look a little bit better. Yikes! Oh man, I have no clue what that looks like. That is awful to type into my calculator. Those of you using the TI-83, be careful on your parentheses. Those of you using Desmos, I have no idea how this goes into Desmos, but probably use some parentheses. Those of you using a TI-84, use the fraction template. Don't do it any other way if you have a TI-84. Alpha y equals, enter. You can type in 6/2 sine of theta minus 3 cosine of theta. Again, if you are one of the people who uses a TI-83, 6 divided by the quantity of 2 sine of theta, and end that parenthesis, minus 3 cosine of theta. I'm graphing both of them. That looks bad. At least they trace over each other, so we know it's good. Alright, I'm going to go to my standard viewing window, and okay. That's actually not that scary. Is that just the line? That's just the line. Looking here, I can calculate my slope. Let's see, the rise is 3, the run is 2, so my slope of this line is 3/2. My y-intercept is 3. This is just the line. Y equals 3/2 x plus 3, right? Am I wrong in this? I mean, that couldn't be that simple, right? Yeah, okay. Cool. I'm not sketching it. No. That look good enough to you guys? It looks perfect to me, right? So here, viewing window. The window, I just use the standard viewing window. Anytime you're using a calculator, if you use -10 to 10 by 10 to 10, you can legitimately just write down standard viewing window, because that is a standard on the calculator. Everybody knows it's -10 to 10. It might take fewer characters to write out. I don't know. I don't like writing, so I always look for the most efficient way to write it. Yikes! 46. Looking at 46, I see I've got an r squared. Looking back at r1 and r2, I cannot plug in r squared because r is my dependent variable. Therefore, I need to solve this for r. Real quick solving is just take the square root of both sides. So I've got r equals the square root of 9 sine theta. Somebody call me on the mistake. Somebody call me on the mistake. Please, you have to use plus or minus because we have that taking the square root in an equation. Now, just calling this back to the lesson for this week, I'm going to say this looks similar to a lemniscate, although we don't have 2 theta in here, but I'm going to guess that this is going to look lemniscate-y. Square root of 9 sine theta, I type that in, and that's the positive. In R2, I need to do the negative. You can just put in negative square root of 9 sine theta, but those of you who have had me in class know that I like to do alpha trace to get the pop-up menu and just do R1 on there. So again, if you have a TI-83, you need to make sure that you type in the negative and then square root of 9 sine theta. It is possible to do the vars in the TI-83, but it's a little bit more difficult. TI-84, you hit alpha trace to get it up there. Desmos, you might even be able to put an r squared. I don't know. Try it. I'm not really that familiar with Desmos. I don't know if I'd call that a lemniscate. Who's going to stop me, right? So it looks like y min, it goes down to x min goes down to -2, goes up to 2. Y, it goes down to 3 and up to 3. So just to make this an almost square window, I'm just going to use the same y min as x min and same y max as x max. And like that. I've got the positive. Oh, that makes total sense that it would look like that, yeah. And I've got the negative. And use whatever you want to call it. Figure 8, lemniscate, I'm gonna do it. I'm gonna do it. Do you want to build a snowman? Doesn't it look like a snowman? Okay, it's not a very tall snowman, but whatever. Window I used was -3 to 3 by -3 to 3. Use the same x min and y min, same x max and y max. There we go. 2 cosine of 3 theta minus 2. This minus 2 really scares me here. I see the 3 theta inside of a cosine function. That draws my mind to a rose curve here, but that minus 2, I don't know what that's going to do. Okay, this is hyperbole. I know exactly what it's going to do. It makes a rose curve, but the rose curve is kind of rotated a little bit off of the axis. We know since we got cosine and we got a 3 in there, we're going to have a 3-petaled rose curve, and if I didn't have this -2, I would actually be straddling the x-axis according to that lesson that we had this week. However, with that -2, we have, it would be similar to a translation on a rectangular graph, where if you put -2 inside of the function, you shift that function either left or right. When we are shifting either what's similar to left or right, we are actually shifting off of the theta. So we're moving our theta forward a couple units here. If you don't understand me, it's just some geeky stuff. And I like to make sure that my rose curves look just nice and symmetrical. So I just did zoom square. You don't really have to. In fact, maybe -2 to 2 in both directions would work well, I believe. Yeah, because that's going to be horrendous to type or to write down on my answer. So let's just go -2 to 2. -2 to 2. And yeah, there we go. And again, those of you who are following along at home, okay, yeah, that's similar to it, right? So yeah, really the joining of the petals should be at the origin, but I'm not really a good drawer. So let's just call it a 3-petaled rose curve. Right? And if you want to be more specific, you might want to point out that the petals actually don't get split by the axis, and the axes aren't immediately in between the petals like the normal untranslated rose curves. If you don't like that jaggediness of the rose curve, which if you're really picky, you won't like it. So if we're being picky, again, we see jaggedness, which is not allowed in a polar graph. We go down to our theta step. We can make it 0.01. Graph slowly, but it graphs smoothly. And actually, looking at that, we can even see that this petal over here dipped down underneath the x-axis a little bit. Okay, cool. Yoinks! 50 looks scary. Oh, wait. That's right. I should put it in my window. What did we ultimately settle on? -2 to 2 by -2 to 2. Alright. Cool. I see secant. I see secant. Don't know how to enter it into my calculator. I am just kidding. I totally know it. See, those French speakers in the room understand that I just set that to the tune of Frère Jacques. Alright, so this is how I'm going to have to type it into my calculator, because I know secant is 1 over cosine. We learned those reciprocal functions so that we could type stuff into our calculators. I think on Desmos you can actually just type in SEC. 4 minus 1 over cosine theta. Typed in right there. You could use the fraction template if you want to, but with just one thingy in there, doesn't really make any sense. Well, that doesn't look... Oh, you know what? I'm still on that goofy viewing window, and it's graphing super slow because I made my theta step so small. Now, you might be able to tell that I stopped the graph from right there. That's if you ever run into a mistake where your calculator's just going forever. To break the grapher, all you have to do is hit on, and it will stop it. And now I can go into my Zoom 6. Looks like a decent thing. Whew. I don't know what that is. One thing to note on here, and here's an instance where TI-83 people will actually have a better knowledge of this kind of thing. That vertical line right there is not actually there. That vertical line is due to a vertical asymptote being here. So there is going to be a vertical asymptote. It looks like at -1 on this. And if I make my theta step really small, like 0.01, where it graphs that really slowly, I can still see when it gets to that Did you guys see that when it graphed that vertical asymptote? It still went really fast. So that tells me that it's not actually there, because the theta step is supposed to be is supposed to make it go so slow when I jump that fast. It's really just the grapher is jumping from infinitely small to infinitely big in a really small amount of time, so it graphs it really fast. So yeah, let's look at that. There's going to be a vertical asymptote at -1. Okay, so you really can't see my graph because I got really nervous when I was drawing my y-axis right there. So just put this guy right here, and then this guy over here. How are we going to describe that? Looks like, oh, if I turn it this way, it kind of looks like Captain Crunch's hat with like a circle underneath it. Looks like Captain Crunch's hat sideways with a not really a circle, a loop. So we have discovered a new polar graph. It is called Looks Like Captain Crunch's Hat Sideways with a Loop Under It. We have made that name official. Window. We just use standard viewing window. -10 to 10 by -10 to 10. I guess you could just put standard viewing window if you want to. STD view wind if you want to do that. Zoom stand, however you want to write it down there. I will point out this is not the official name for this. People have seen it before. It's in your book, so yeah, lots of people have seen it before. Okay, looking here. R equals e to the theta over 2. Well, I'm going to point out that this actually looks like an exponential function, something that you guys learned earlier this year. And we remember an exponential function kind of just like grows exponentially. It gets really big really fast. So I'm going to say that this is going to imply that the radius gets really big really fast as you rotate around here. So looking here, I'm just going to type it in. E to the theta over 2. Okay. You guys really have to tell me when I change that theta step to something. Whoa. Look at that. It kind of looks like the spiral of Archimedes, right? So the spiral of Archimedes you guys saw in the video for the lesson. And the difference on this from the spiral of Archimedes, you can see the spiral of Archimedes, if I put it on a square viewing window, I just did zoom 5 there. Spiral of Archimedes kind of moves away from the axis at a steady pace because it is a linear, well, analogous to a linear function. The spiral that we have over here actually gets bigger really fast. I mean, look over here how much bigger it is, how much further from the origin it is. So just looking at that, just real quick sketch. Yeah, cool. And let's just call it an exponential spiral. All right. Window we use goes, again, standard viewing window. Yeah, that's what I thought. All right, so we're done with the first part. Second part says to graph these and find the domain such that you can trace the figure exactly once. So we're going to type these in, and we're going to do some playing to figure that out. All right, so I got 2 times quantity of 1 minus 2 sine theta. Well, my mind on this one goes to, again, my favorite curves, the limaçon. I could distribute that too. I'd have 2 minus 4 sine theta. Looking at my limaçon curve, since my A is smaller than my B, this is going to be a limaçon with inner loop, and a limaçon with inner loop has a domain from 0 to 2 pi, but just to be clear, I've got 2 times quantity of 1 minus 2 sine of theta. Again, I'm just going to rely on my technology to see this one. Okay, so I do see that it is a limaçon with inner loop. The one thing that I want to see on this is if the function actually continues past that 2 pi. So what I like to do here is just to make theta max something ridiculously high. And I know what number we all think is ridiculously high, 20. If you don't think that's ridiculously high enough, go up to 50, 1,000, whatever. But the higher you make your theta max, the longer it's going to take to graph this. So I hit graph, and look, and I can see it spinning up here, and it's still graphing the exact same thing. So it looked like when I was using the standard viewing window that it went from 0 to 2 pi, but here I can just verify that. Again, at 0, I start over here. I'm just tracing around this curve to figure out one iteration around the curve to get back to that point. And there, I'm back at that point. And look, it's right at 6.2831853. So here, do we actually have to sketch it? No, we don't even have to sketch it. All we have to do is say the domain that we wanted to use went from 0 to 2 pi. I guess technically you'd want to make one of those exclusives, so like inclusive on 0, exclusive on 2 pi. So I guess technically the best answer, those math geeks out there will know that I should put a parenthesis right there. 3 sine of 5 theta. Well, I see that 5 with a theta inside here, so it draws my mind to the rose curve, but this divide by 2, I don't really know about it, because all the rose curves that I had on the lesson involved integral values for our n there, and we all know 5/2 is not integral, so I don't know what's going to happen here. Let's go 3 sine of 5 theta over 2. And I'm going to go back to the standard viewing window, so I'm going to go back to 6. I can see it looks like what a 5-petaled rose curve right there. That's weird. And it's like a really lopsided 5-petaled rose curve. Again, I'm going to point out that I did use the standard viewing window, which doesn't graph this whole thing, all that I needed to graph. I need to go even further to get the rest of this graph. I need to go higher than 2 pi. So again, I'm going to use something ridiculously high. Woo, not 200. That's unimaginably high. 20, though, is fairly high. And I can see it's still spinning, and it's still just looping back on it. So I actually have the full domain here. Now this, I know I'm going to have to experiment with this one to figure it out. So I want to get to this place and coming out on that. So like, I want to figure out where do I come out onto that first petal right there. Just trace. I want to sketch over every single petal. So I got some of those petals around. Okay, so I'm still not back to that first petal there. Still not back to that first petal yet. Oh, hey, look, I'm back on that first petal. So I know I want to go to where I'm at the origin. I'm at 12.566371. From 0 to 12.566371. I hope somebody is jumping out of their skin right now to recognize that this is not actually accurate. This is a rounded form of the answer. All of these are going to have domains that are similar. They're multiples of pi is really what we're looking at, because we're looking at the periodic nature of these trig functions, which have multiples of pi as their periods. So here, I just do a little bit of experimenting. I said quit. I hit 4 pi. Notice how 4 pi is almost exactly the same thing as this. Yeah. The real domain, if we want to be accurate, goes from 0 to 4 pi. Right? And last but not least, we got r squared again. R, therefore, is going to be equal to the plus or minus square root of 1 over theta. Now, I just want to point out here, there are a couple things that I know about functions from rectangular coordinates that stick in polar coordinates. One thing is you can't divide by 0. So I know 0 is not going to be in the domain of this function. I also know that I can't take the square roots of negatives. So I know negatives are not going to be in this domain. I know the domain is going to go from 0 exclusive up until we find a place where it traces over. Now, I don't know when I want to tell you this next thing that I want to tell you. Whoopsies. Negative R1. Okay. So I'm going to graph this. Okay, cool. Alright, it just kind of like comes in and it starts squiggling down into the center there. It didn't really look like it was tracing over top of itself. Let's make this really, really big. 200. Alright, unbelievably big. Okay. So it looks to me, as it squiggles in there, it never really loops over on top of itself. What we look at here is what made these have domains where we would have to restrict them to get one iteration over the curve is these periodic functions. Sine, where it started producing the same values again. I don't have a periodic function up here. I've got square root of 1 over theta. The bigger you make theta, well, that makes this fraction smaller and smaller, but it's never going to loop back onto itself. So I'm going to say the domain is from 0 up to really, really big, up to infinity. There we go. And there is your second homework video. Sorry it ran a little bit long, but I really have fun with this stuff. See you guys later.